Hey everyone. In this video, I'm going to review some of the basic methods in mathematics and probability that we're going to need throughout the rest of the semester to both derive and understand the regression models that we're going to work with, okay? And I want to note that a lot of the material that I'm going to go through in this video is kind of a review and summary of concepts that we talked about in the previous semester in POL 701, right? So if you want some more detail and more elaborate explanations of some of the things that I'm going to talk about in this video, make sure to check out the videos from last semester on probability and uncertainty. If you want some more detail, some more examples, and some more elaborate explanation of some of the concepts, okay? So with that, let's get started. And the first thing that we should talk about, we already talked about it a little bit in the last Q&A session, is this conceptualization of probability. What does probability actually mean as a mathematical concept? And what probability is ultimately it is a model of uncertainty. And as we discussed, it has ultimately two alternative interpretations of how we think about what probability ultimately represents, okay? On the one hand, we have the frequentist interpretation. And this frequentist interpretation, which we kind of focused mostly on in the previous semester in 701, is based on this notion here. Uncertainty is based on this notion of repeated experiments, right? And so we're kind of thinking about probability as describing chance over repeatable events, and we're kind of approximating the relative relative frequency of an event occurring over repeatable or over repeated experiments, okay? So in other words, probability in the frequentist sense represents the limit of the relative frequency with which an event of interest occurs when the number of experiments repeatedly conducted under the same conditions approaches infinity, right? So we have this underlying notion of probability as based on repeated experiments, repeated events occurring, and the probability that ranges from 0 to 1 ultimately represents the relative frequency of that event over repeated experiments or repeated data generating processes, so to speak, okay? And then on the other hand, we have the Bayesian interpretation of probability, right? And here we're not talking about repeated experiments and the relative frequency over repeated experiments, but rather the Bayesian interpretation of probability is one of a subjective belief, right? So probability here is a personal measure of uncertainty, okay? In other words, probability is a measure of one's subjective belief about the likelihood of an event occurring, okay? And so it's not grounded in this idea, or it doesn't require this idea of repeatable experiments, but rather focuses on people's or the researchers' kind of subjective belief about an event occurring and kind of quantifying that belief, okay? Now, you might kind of think that that might be problematic to bring kind of like subjective beliefs into kind of scientific inquiry. But on the other hand, one can argue that kind of incorporating prior beliefs and thinking about probability as a subjective belief, ultimately, well, it has two advantages. One, this idea of repeated experiments, while it is kind of useful in an ideal world where we can think about, repeating a survey 100 times, 1,000 times, and so on, oftentimes we have scenarios, and as social scientists, we're interested in scenarios where this idea of repeated experiments doesn't really apply. So, for example, if we want to think about like what is the probability of, Biden winning re-election 4 years from now, right? That's a one-shot event that it's a little bit hard to think about that one event as potentially being repeated, and then thinking about the probability as kind of the the relative frequency of that event occurring, right? So from that perspective, this Bayesian interpretation is kind of more applicable to a lot of scenarios where we only have single events, but we're still interested in probabilities, okay? And then on top of that, even though we're thinking about probability from a Bayesian perspective as a subjective belief, we're still kind of, and we'll go through that throughout the semester. There's still clear rules of how we incorporate these subjective or this prior information, right? So, in other words, it doesn't really contradict kind of our ideal of scientific progress because there's still clear rules of how we incorporate prior information. And in other words, two researchers who have the same, prior belief and collect the same data would ultimately still end up at the same conclusion based on, a Bayesian interpretation of probability. Okay. The other thing to keep in mind is that these disagreements between frequentist and Bayesian statistics are ultimately disagreements about interpretation. There are some other, aspects or implications when it comes to, computational questions, but ultimately it's about interpretation and the mathematical properties of probability. Whether you're, a frequentist or a Bayesian, are all driven by the same axioms, and the rules of probability, so to speak, are the same, right? One of the fundamental ideas of Bayesian probability is relying on this, as I said, this measure of subjective belief in an event occurring. Okay. And so from this perspective, it's pretty natural to ask, okay, so how should I update my belief after I observe some new data? Okay, so I have some prior belief about an event occurring, and then I, collect some additional data, and then I should update my belief. So how can I do that, right? And in order to do that, we use Bayes' rule, okay? And Bayes' rule shows kind of analytically how we can update beliefs in a kind of a mathematically coherent manner, okay? Going back to last semester, we talked about conditional probabilities, and from the basic conditional probability formula, we know that a conditional probability of event A occurring conditional on observing B, so probability of A conditional on B, can be expressed as the joint probability of the probability of A and B occurring, divided by the marginal probability, so the probability of B occurring marginalized over whether A occurs or not, okay? And now, using the multiplication rule and the law of total probability, we can basically express this fraction between the joint probability and the marginal probability as two conditional probabilities. One, the probability of A intersect B can be expressed as the probability of B conditional on A times the probability of A. And then the marginal probability can be split up into the probability of B conditional on A times the probability of A plus the probability of B conditional on A complement, so A not occurring, times the probability of A complement, okay? And so that's basically already Bayes' rule. Bayes' rule gives us a way of computing the conditional probability of A conditional on B based on the probability of A, the overall marginal probability of A occurring, the probability of B conditional on A, and the probability of B conditional on A complement, right? So in other words, putting this back into this Bayesian perspective of prior beliefs and how we kind of update our prior belief and form a posterior belief, we have our prior belief A, the probability of A. We observe some additional data, which is the kind of the probability of B conditional on A. And based on that, we can compute our posterior belief, so the probability of A conditional on B. So after we have observed our data, okay? So regardless, and keep in mind that Bayes' rule kind of applies, like this rule of computing conditional probabilities applies whether or not you think of kind of interpret probabilities from a Bayesian perspective or from a frequentist perspective, right? So regardless of whether we interpret probability as a subjective belief, Bayes' rules shows mathematically how the knowledge of our prior probability, so the probability of A, as well as the kind of, we could think about it as the likelihood of observing our data, that's the probability of B conditional on A. So we could think of that as the likelihood. And the probability of B conditional on A complement, so A not occurring. All those combined yield our posterior probability, so the probability of A conditional on B, so conditional on after having observed our new data, what is our new belief about the likelihood or the probability of A occurring, okay? So that's a little bit of a review for this concept of probability and how it relates to kind of Bayesian statistics and frequentist statistics. Again, the main differentiation or the main difference that you have to keep in mind is, on the one hand, probability being based on this idea of repeated experiments and thinking about probability as the relative frequency of an event occurring. That's this frequentist interpretation. And the Bayesian interpretation, which conceptualizes probability as a measure of subjective belief. But what I want you to keep in mind, despite the fact that we're thinking about probability as a measure of subjective belief, it doesn't mean that this Bayesian interpretation is somehow less scientific, because we still have clear mathematical rules of how we update our beliefs given what we thought prior to observing any data, and then how we update that prior belief after observing new data. And again, despite the fact that we think about this as a subjective belief, two researchers with the same data and the same kind of prior belief that they specify still reach the same conclusion in a Bayesian framework. Okay, the only difference is that we're more. You could say that the only difference is that we're more explicit and kind of make explicit what our prior beliefs are, and incorporate them directly into our model. And in that sense, that's a step forward from the frequentist perspective. Okay, I'm going to take a quick break here, and in the next video, I'm going to continue our discussion of basic concepts in probability theory with an overview of random variables and probability distributions.